right. This is the continuation from the exploration I was doing 2 days ago. We were looking at polynomials, and there are a few things I was looking at. We looked at this forward difference operator and just a forward operator, where we take a polynomial px, and we see what happens when we plug in x plus 1, and we get out a new polynomial, and we express the coefficients of the polynomial in terms of the old polynomial. And that sort of motivated me to look, okay, well, what happens when we look at evaluating polynomials at roots of unity? We saw that we basically just got the Fourier transform of the coefficients of the polynomial. So that was kind of neat. And today I want to explore that a little bit further. Now let's see. Let's share my screen. All right. There's one thing I wanted to do. Namely, we had this operator that took us from px to px plus 1. And I think I just called this an operator. Actually, let's call this, what's a good term? Let's just use T for translation. So that's effectively what we're doing. Now, this operator is really an operator, meaning that you can interpret it as a linear operation, linear map on a vector space. And of course, here the vector space is the vector space of all polynomials. And you can check that this is a vector space, is closed under addition, has a 0, and is closed under scaling of either real or complex numbers or rationals. Every time you have an operator, linear operator, you should think, okay, is there maybe a nice basis in which to express this operator in? So that's one thing I want to have a quick look at. And maybe to make that clear, sort of the standard basis for polynomials is just given by all terms of the following form. Sorry. Right, all the collection of all x to the power i's, these monomials, these form a basis. So, and we saw that performing a from this translation operator takes this basis to or it has a very specific action on this basis. Now, last time I sort of looked at a general expression. I wrote down a general polynomial to form x of I, x to the I, and then looked at what ti did, or sorry, what the t operator did. But it was at a very specific basis, and we got out something nice. But it would be nice if there's, for example, an element in this vector space that is invariant under the translation operator. And there's actually well, I guess one observation we can make here is the following. I believe that no finite sum of monomials will achieve this, because what we really want to ask, oh, actually, now that I come to think of it, yes, what I had in mind is asking, okay, does there exist a polynomial such that this holds? But this is, of course, an eigenvalue. This will be an eigenvector of t with eigenvalue 1. But this might be too strict. Maybe we can have a lambda here. Now, I want to first go to an example where it's really an eigenvector with eigenvalue 1. And there's a very nice geometric way of thinking about this. I just realized if you just, we translate we have a function, which is some polynomial. And if we translate it, we should get out the same value or the same function. Well, these are just invariant or translation invariant functions, like cosine and sine. And one thing I just realized is that I've been calling these things polynomials, but of course, when we go to a sum of these monomials, an infinite sum, then in general, we should really be talking about a series. So I might be I might be a little bit careless with that as I'm working on this. Okay, so let me quickly check what the previous expression was that we had. So, okay, let me just copy paste this. I'm actually not sure if I can copy paste between two different notebooks. Let's see. Just quickly move this here. All right. Let's see if there's a nice way of expressing it this way. Aha. Okay. I guess already one thing we can see from here is that I saw this expression and I thought, okay, equating these things equating this to the original coefficients to find the eigenvector. That's one way of doing it, but it seems a little bit messy. And one thing I just realized is that, okay, one thing we can do is look at this equation right here. And I can keep on repeating this t operator. So if I hit this guy, let's see, is that true? Let's quickly see. Let me think for a sec. What I wanted to do was the following: say that this is equal to lambda times, let's call this P2. Let's add a subscript here. And then I wanted to hit P2 again with this T operator. Oh, my bad. See, I'm making a mistake here. There shouldn't be a +1 here. What we want to have is that this is really equal to px. Okay, now we're good. This makes more sense. Yes. Right, every time, this is very silly. Every time we apply the C operator to an eigenvector, we just scale it with this lambda parameter. So in particular, if I repeat that, let's say n times, I just multiply with lambda to the power n. The lambda to the power n, that's really just an exponential, right? I'm scaling with some scaling factor. But that's exactly what exponential behavior is. And so let me be more explicit about this. Oops, not a t, that's a 1. Where I'm trying to head at is that we definitely won't get a finite, assume lambda is non-zero. Then what this tells us is that we really get, lambda might be 1 or 0 or maybe -1. Let's see. What I'm trying to get to is saying, okay, if we move by, let's say, k steps, or n steps, we apply the translation operator n times. That also means that we're really just scaling. We are getting exponential behavior. Now we know that exponential behavior doesn't arise for any finite polynomial, because we know that the difference operator, or the forward operator to a polynomial, gives us another polynomial. Let's see, is that sufficient argument? Okay, I'm not sure how to make that precise, but I wanted to sort of use this argument that, okay, we cannot get any really finite polynomial or finite series. We should really get an infinite series, and we should reclaim the exponential functions, I believe. So one thing I for sure know is that if we have something like this, and then under the Z operator, and again, note that this is really a series, right? So we can think of this as an infinite polynomial, and oops. One, this just gives us to the A times X plus A, but this is just E to the A times E to the X. And so this is our lambda, right? So we see that we get the desired behavior here. Let's see. And here one can already sort of reconstruct that these are all the functions, since they should form a complete basis. And I guess what we're really doing is we're recovering the Fourier series. Okay, I guess in hindsight this is not too surprising. So let's move on. Okay. Let's try to do something else. Yeah, so last time we had a look at what happens when we evaluate roots of unity for polynomials of degree d. And we saw that we recovered the Fourier series of the coefficients. So that was nice. I wanted to do a little bit further exploration. Namely, if we have on the left-hand side, we have sort of the original polynomial. And here we have the Fourier transform picture. So we just plug in here the roots of unity. I want to sort of relate these pictures. And one thing that we found is, when we had this series where we just have a constant term, then of course we get here up to scaling, something very uniform. And that makes sense, right? If we have a constant polynomial and we evaluate it in terms of unity, we should get out constant values. So that's what we're seeing on the right-hand side. And similarly, if we have something like this, and these are the coefficients of our polynomial, then we just reconstruct a geometric series. And indeed, when you evaluate it at the roots of unity, you get out 0, except for the first entry, which is some scalar. I believe it was d plus 1. So that was sort of a nice way to see this. And one thing I was curious about is, okay, we can have a list of coefficients here that is even. And this should translate to a Fourier transform whose coefficients are purely real. And similarly, if we have here something that is odd, then we should get something that's purely imaginary here. Right, so this is something we know from standard Fourier transform, but I just wanted to write this out explicitly to see what happens. Okay, so let's see. What does it mean to be even? Well, if I have some coefficients AI, this means that AI is equal to AI. There's this annoying +1 factor. Let's see if I'm getting this right. I think it should be this. And for minus, for if it's odd, we just get a plus or minus here. Let's see. Now, what can we really say about this sort of non-trivial? Okay, I guess this suggests that we should group certain terms together. Maybe just AI and A sub d plus 1 minus I. Okay, because if I have terms like that, right, I pair those guys together. Let's see, d plus 1 minus I, and I plug in a root of unity. Is there a nice way to simplify this further? Okay, yes, this is maybe not the nice way to write this. If we're going to plug in roots of unity here anyway, then we can just remove this term here, right? Just because of the sort of cyclic property of roots of unity. And what we just get out here is this will be proportional to xi plus or minus x minus I and plug in roots of unity. Okay, so this is okay. This doesn't really tell us too much anything too interesting. Let's see. Okay, let's try to do something else. So we know that for fixed d, we know that the polynomials with even and odd coefficients, they form a vector space. Let's double check this. I'm just worried about the zero polynomial now. Okay, the zero polynomial is fine. It's in both. Okay, right. So this sort of makes sense. We have our for fixed d, we have our vector space splits naturally into sort of two vector spaces, the odd and even polynomials. Now, it would be nice if our polynomials are also, these different subspaces are also closed under multiplication. Right, because then we can say that we really get some odd and even algebra. Okay, so let's just do a quick dirty calculation. I'm just going to do something like this. Actually, let's be very explicit. Let's make out let's write down the general case. So I have two. Right, if I have two polynomials, this form, I multiply them together, then what we get is another polynomial with coefficient c sub I, where c sub I is given by the sum. I believe this is called the Hadamard product, if I remember correctly. maybe not the Hadamard properly. No, the Cauchy convolution, I believe. So we fix I here, have J here, and then we take all the AJ times B I minus J. Okay, so let's see. Okay, I'm going to write a general case for D is, let's say, 3. Yeah, let's do D is 3. Okay, so we just get out something like this. Okay, so this is, of course, this is C3, right? This is C3. And if we want to get out an even function, then we want that C0 is equal to C3. Let me double check if I'm doing this correctly. Let's plug it in here. So I is 0, D plus 1 gives me 4. See, I'm making again mistakes with the indices. That's very annoying. No, this is correct. We want that the actually, it's not actually clear to me what the right definition of odd and even is, because here I have my first entry, my second one, my third one, etc. And do I want this to be symmetric around like this axis here? Or maybe more naturally, I want it to be sort of symmetric. You know, if I think of this as a list of numbers, as a cycle of numbers, that's sort of symmetric around this axis. Now, I'm not too sure. It might be that those are also the same. No, that shouldn't be the case. Okay, this makes sense also with what we saw here, because the D plus 1th entry is again the 0th entry. Yes. Okay. Okay, I see. Yes, that makes sense. Yes, so I do want this to be symmetric, sort of around this axis here. Okay, that's good. That was a good sanity check. So indeed, we want C0 to be equal to C3. Now, what is C0? Aha, I see. Okay, yes. Okay, in hindsight, kind of obvious. The statement, as I initially stated, does not hold. What was the statement? I said I wanted to check for a fixed D. If I multiply two polynomials in that vector space, do I get, even polynomials? Do I get out something that's even again? And in particular, do I get out something that's again in the vector space of polynomials of degree at most D? But that's obviously not true, right? If I take 2 degree D polynomials and I multiply them together, then I get a degree 2D or 2D plus 1, something like that polynomial. I think 2D. So that statement does not hold. Now, is there a way to sort of salvage this? Let's see. So I guess one thing that we can use is that when we plug in a dth root of unity, even in a polynomial that's not of degree 2, we sort of take our polynomial and we sort of, how to say, well, let's write this out. I have some degree, let's say d prime, where d prime is greater than d. And if I plug in now a dth root of unity here, it will, I can rewrite this as sum only ranging over d. With now some different coefficients. Trying to be consistent with my notation here, but let's see. And what are these BIs now? Well, the BIs, they are going to be the sums of all the AIs. Let's see, all the A sub j's, such that j is equal to I modulo d. Maybe d plus 1, let's see. No, this should be correct. This should be correct. I'm also thinking now whether it's just more natural to consider d minus 1 polynomials instead of d polynomials. Again, indices are always my bane of my existence. Okay, but let's assume we have this. So this is sort of a nice way to take some let's say d prime polynomial, and by plugging in these roots of unity, we sort of force it back to a, not really a polynomial, degree d polynomial, because we've now inputted very specific values for x, namely these roots of unity. But we can always think of the statement that we have there's always a degree d polynomial, such that when we input these values, these roots of unity, we get out the same value, right? And that's going to be exactly this polynomial given by these coefficients here. Let's see. Yeah, and I guess that also brings me to the sort of following statement. If I have some function of x, and I don't know a priori whether it's a polynomial or not, or a degree d polynomial, and I think like, okay, well, the only thing I could do is I can evaluate it at certain values, and I just want to see what comes out of it, and I'm going to make an estimate, I guess, what the Fourier series of the list of coefficients would be. Again, I don't have a prior knowledge about whether it's a polynomial or a degree d polynomial, but let's just see what happens. Now, one thing that could happen is that if I plug in these roots of unity, I always get out 0. So naively, I might think, hey, this is really a this function is really 0, but this doesn't have to be the case. For example, f can just be a polynomial of the following form. Let's see. And of course, when we plug in nth root of unities here, let me fix that. Then we won't see that. Okay, so how can we think of this? If I have a function, okay, yes, this sort of also ties in together what we were thinking about here. If I have some function, f of x. And let's make this a little bit more abstract. If I think of this as some function that takes in, let's say, values in. Let's be sort of specific. I have some ring here, and this goes again to some ring here. Okay, this probably, let's fix this to be a polynomial. This should probably be a polynomial. Okay, let's restrict to polynomials. So I have some ring, and I have some polynomial over that ring. I can now evaluate a polynomial at certain values of x. So for a given f, I have I can evaluate x at some value. Let's say xy, I guess. Again, I'm not sure if this is standard notation, but this should get the idea across. So I just take my polynomial and I evaluate it at x equals y. The nice thing is that this is a homomorphism in the sense that here we have a ring and we can scale it. We can add numbers together. We can also multiply two elements together. And it doesn't matter, right, the order in which we do this. We can either, if I have two polynomials and I multiply them together and I then evaluate them, that's the same thing as first evaluating these polynomials together and then multiplying their outcomes. So this is really a homomorphism. And what this tells us is that, okay, if we, let's see, so that gives us one homomorphism, right? We go from R to Rx to R. I can also now do the following. I take some f. Actually, let's stick with p since we're doing polynomials now. I can sort of take the above homomorphism and extend it to and apply it, let's say, d plus 1 times, where now the evaluations are at very specific values, namely the dth root of unities, or the d plus 1th root of unities. So I'm going to call this f for Fourier transform. And what I'm doing here is I'm just calling the eval function, or applying the evaluation homomorphism on each of the entries for the different roots of unity. Now, this is clearly, again, a homomorphism. Let's quickly check that. So it's definitely a homomorphism on vector spaces. It's not clear to me if it's really a homomorphism with the multiplication structure. Let's see. It should be, and let's see, I'm a little bit confused about this because, or at least I think we should be able to phrase this in terms of the convolution, right? Because we're doing a Fourier transform, and we know that multiplying two functions together, then taking the Fourier transform, it's the same thing as first taking the convolution of these functions, and then evaluating the Fourier transform. Okay, but it checks out because the convolution of two polynomials is just really their multiplication. Right, so normally when we think of the Fourier transform, we just say, oh, we have a sequence of numbers, but we don't attach any further algebraic structure to them. But here, the algebraic structure, right, the multiplication on these list of coefficients is just given by the associated multiplication of the two polynomials. So that checks out. Okay, let's see. So we have this homomorphism here. Now we can think of what does this statement mean. We have here, you have a polynomial of this form, p of x. And I evaluated the roots of unity. We get out 0 entry-wise. So these functions are really in the kernel of that map. I guess I should be clear here. This homomorphism here is, of course, for a fixed d. Right? We're evaluating at specific roots of unity. And now for a given d, we will have elements that are in the kernel. Now let's see. I claim that these polynomials are all in the kernel. But are there more of them? Let's see. So I guess here we could try to think of this purely in terms of vector spaces. But I believe the nice thing is that we not only does this kernel form a subspace, but it should be actually an ideal, right? Because if we multiply this px with some other element, then if we evaluate px times some other polynomial, let's say q of x, it will still evaluate to 0, just because p of x it will be 0. I think technically we require, what is this? This is an integral domain, meaning that if you, maybe I'm mixing things up, but if you take two elements and then they evaluate, well, okay, one of them is 0, then the product needs to evaluate to 0. Okay, yes, I think an integral domain, it might be that if you have two non-zero elements, you multiply them together, you can get the 0 element, but that's not the case here. Okay, yes, okay. Okay, so we know that we can really think of the ideal associated with this homomorphism here. And the question that I now have is this ideal, it's called I, is that generated by x to the d? Again, I will be very careless with the plus ones from now on. But the question is this generated by this polynomial here? My initial guess would be yes. Let's try to see if we can prove that. So what is the statement that we want to make? Let's see. So what does this mean? If I remember correctly, these are all I take all polynomials. Let's see. I'm using the bar to indicate all polynomials now. Or I guess series, really. Maybe we might want to be a little bit more general. And I just multiply this by x to the d minus 1. So for sure, we do know that this is in I, in the ideal, right? Because again, if we plug in root of unity here, then this whole thing will be 0. But what happens? Can we show the other inclusion? Okay, so what does this mean? I want to have some p of x, and what do I know? I know that when I plug in roots of unity, I get out 0. Okay, if p of x is really a polynomial, meaning it has finite degree, then it means that the roots of unity are really roots of this polynomial. And then we're done, because that means we can, right, any polynomial we can write as a finite product. Let's use d sub I here. And this is a product, by the way, in case that wasn't clear. But we know that there will be at least one occurrence of the roots of unity for its di's, meaning we can divide this polynomial by p of x. or by, sorry, let me be explicit. So this really means, that, oops, x to the power d minus 1 really divides p of x. Okay, so that's good news. That's one thing I wanted to check. So, okay, at least if we assume that p is of finite degree, really a polynomial, then it is really in this ideal. Now, it's not clear to me, so that argument doesn't work when we have a series. So let's see. Okay, that becomes a lot harder to show. Okay, maybe slightly different. Let's see. I'm wondering if this somehow relates to the cyclotomic polynomials. Now, if I remember correctly, cyclotomic polynomials are polynomials. They are the, let's see. Oh, I forgot the term. I think it was minimal polynomial. These are the minimal polynomials of the d root of unity. So these are the smallest, or the smallest, I'm not sure exactly which sense, but sort of the I guess the irreducible polynomials that have the d root of unity with integer coefficients as a root. Okay, let me quickly check online. I don't want to do everything completely by myself. All right, so let's have a look. Okay, let me share my screen because you cannot see what's happening, of course. All right, so it's a unique irreducible polynomial with integer coefficients that is a divisor of x to the power n minus 1. So that is quite, okay, does seem quite nice. So these are all the primitive roots of unity. So primitive roots of unity are, they generate the whole group of roots of unity. Let's see. Okay, let me go back to my iPad. So of course, if we say we just evaluate the Fourier transform at the primitive roots of unity, then indeed the cyclotomic polynomials would appear. Now, the cyclotomic polynomials are are quite interesting. I sort of encountered them before, so it would be nice if we could sort of force them into our problem. And so I'm curious what it means, right? Let's flip this around. I take some, let's go really to the Fourier picture. I have some sequence of numbers, and I calculate now the sort of the Fourier transform, but only at the primitive roots of unity. Let's see, does this make sense? Okay, let's have a quick look. We get out something non-trivial. Okay, so let's look at DS4, and again, I'm being very careless here with indices. X squared plus 1. So this is the cyclotomic polynomial of degree 4, or sorry, not degree 4, but the nth, the fourth cyclotomic polynomial. Let's see. So let's quickly check this. What are the primitive roots of unity? Oh, it's just generated by I, and when we plug in I here, then we get out exactly 0. Okay, so that makes sense. Let's see. And -1 is not a primitive root of unity, right? Because it does not generate the whole group. It only generates a subgroup. So, okay. Let's try to be very explicit. I have some sequence here of coefficients. I evaluate now the roots. Sorry, I plug in the polynomial now, not for all roots of unity, but just for these primitive ones. Let's have a quick look if I remembered the definition of primitive correctly. Let's have a look. Okay, so I realized that for future recordings, it will be nice if I can more easily switch between my screen on my computer and my iPad, because I'm now looking at the at my computer. Okay, this might be interesting to investigate later. So of course, I don't expect that just by plugging in the ith root of unities, or the primitive roots of unity, that we recover the full information. But I hope that we would recover at least some important information. And the question is really, what do we recover? Okay, so for x4, we have two primitive roots of unity. We have I and minus I. Let's go to 6. 6 is maybe a little bit more interesting. So on the complex plane, I can think of my roots of unity as laying somewhere here, say, 3, here. Okay, this is very, okay, yes. One more time. We have here root of unity, here root of unity, here root of, no, not there, but here, here, and here, and here. Now this is definitely primitive root of unity. This is not. One way to see that is that it right? This is sort of this is the 0th root of unity. This is the 1 root of unity. It's the 2nd root of unity. That's 2 is, of course, divides 6 non-trivially. Same thing for here. Not a primitive unity. Not a primitive unity. Oh, okay. So it's just 2 roots of unity. Let's double check that. If I look, yeah, this makes sense. If I look at the 6th cyclotomic polynomial, it has this form, x squared minus x plus 1. So it has degree 2, which corresponds to the fact that there's just that there's just 2 primitive roots of unity. But here we get quite limited information. Okay, so let's take a step back. I said, okay, I want to limit myself to a sort of Fourier transform where I only put in roots of unity. So how can we formalize that? Well, what I really want to do is something similar to what we did here. Here, I said, okay, we are evaluating a polynomial at, or again, maybe a series. I'm being very careless with that now. And I apply this homomorphism, really this ring homomorphism from our set of polynomials to a sequence or a vector space of the complex numbers. And here what I did is, okay, I had really D entries, right? So my vector space has dimension D. But now my underlying vector space will have dimension only 2 in this case for the case of degree 6. So now we have a map that takes us from polynomials to, well, let's see, what is the okay, to some vector space, must be very explicit here, c to the power, and let's see, here we want to count the number of primitive roots of unity, which is, I guess, given by the Eulerian some function. What was it again? It's the Euler-Tauschen function. This is phi, and we plug in here d. And so Euler's Tauschen function just counts the number of primitive roots of unity, or the number of elements that are not wait, what was it again? That are co-prime. Yes, that are co-prime with D. So it's also the degree of our cyclotomic polynomial. Okay, so we want to understand, is there a nice way to think about this? And as before, this is still a homomorphism, a ring homomorphism. And we should now try to answer what kind of structure does this carry. I guess one thing that we could do after that is that, okay, if we sort of understand the information here, we could look at the ideal. So here again, the ideal should be generated again by, I believe, by the cyclotomic polynomial for a given D. And what we can then do is we can quotient out all the polynomials by the cyclotomic polynomial, or by this ideal generated by the cyclotomic polynomial. And okay, I guess the kernel, okay, yeah, I'm not really saying anything new here. What I want to do is, if this is indeed really true, I want to relate what this ideal, and I want to quotient out by this ideal. I would want to then understand what is then the the ring that we have left, what kind of structure does that have? I'm actually not really sure already, right? If we take all our polynomials p bar and we quotient out the ideal, I always forget which order it is, which direction the slash is in, but let's think it's this direction. So quotient out by this ideal, what do I then get? All right. Well, I think for now, this is just a good place to stop.